How do we find the maximum power transfer to a load? Again, I'm asking, I want to make sure my load has the maximum power transfer. I could have any circuit I want in the, for example, I'm not going to solve this yet, but I could have a circuit that looks like this. Some voltage source here, I won't even give you numbers, and a resistor there. Down with the resistor. I could have some dependent current source, voltage source here, doesn't matter. And let's say I have a resistor here, we'll call the load resistor, R sub L. I don't want to give you numbers intentionally. And the question is, what value I need to put for R sub L to get a maximum power transfer to that load? That's what the definition, maximum power transfer to the load. So what should we make R sub L equal to? First, when I have a problem like this, maybe what I want to do is Theveninize that problem. Find the equivalent Thevenin circuit. So if I Theveninize all of this, my circuit will look something like this. V Thevenin, R Thevenin. What I should have done with R sub L, I should put a line going through it. What does that mean, that line going through it? If you see that in a book, that's an adjustable resistor. You can turn it, change the value on them. I don't know if you use them in our lab. We have something called pot. Yeah. It's round one. You turn the knob. You can go from, I think the one we have in the lab, 0 to 5K, I think. If I remember, I don't do the lab anymore. You can adjust the value of that resistor between 0 to 5 by turning it left and right. So this is an adjustable resistor, so that changes. This doesn't, that doesn't. So I want to calculate what value for R sub L, if I put it there here, I will get the maximum power sent to the load. Any other value, if I put a bigger one or smaller than the one I'm going to calculate, I will not get maximum power to the load. Question, Tyler, or stretching?
Oh, I'm stretching.
Okay, no problem. I just know if you have a question. Okay, so let's look at that circuit. What is the power to the load? L, we'll call it to the load. You can calculate the power by taking what? V times I. You can calculate the power by taking what?
R.
V squared over R. Or you can take the power by multiplying I squared times R. Well, finding I is going to be easy here. I will be what? Isn't that V Thevenin divided by the sum of these two? Ohm's law. You can combine these into one resistor, and the current will be the voltage divided by R. So the here will be I squared times R sub L. Well, I is what? V Thevenin over R Thevenin plus R sub L. You're going to square that times the value, which is R sub L. Now, that's the power shipped to the load. I didn't say maximum yet, but that's the power. So it's V Thevenin squared times R sub L over R sub L plus R Thevenin squared. And now let's bring in calculus. The question says maximum power transfer to the load. Maximum. If you want to find the maximum or the minimum value in calculus 1, if you remember that, what did we do? How do you find where the min and max going to be?
Find critical values.
And how do you find the critical values?
Set
take the derivative and set it equal to 0. So I'm going to take, the only one that's changing value is r sub L. So I'm going to take my derivative with respect to r sub L. So what is the derivative? dp dr sub L. Taking the derivative with respect to r sub L. Notice I have a fraction. When you have a fraction, you want to take the derivative. What rule do we use in calculus? The quotient rule. The bottom times the derivative of the top. I'm taking the derivative with respect to r sub L. So that's v thevenin squared. Minus the top times the derivative of the bottom. Now, since the power is 2, I have to use the extended power rule, which says what? 2 times r sub L plus r sub thevenin to what power? To the power of 1 times the derivative what's on the inside. What is the derivative of r sub L? 1. What's the derivative of r sub theta? 0, because that's a constant. That doesn't change. R theta, or r thevenin and v thevenin are constant. Their derivatives are zeros. All of that divided by the bottom squared. That would be the 4th power. You square the bottom. Again, for maximum value, or minimum, you want to set the derivative equal to what? Equal to 0. So let me take my derivative and set it equal to 0. Well, when you have a fraction, and you want the fraction to have a value of 0, the only way that will happen mathematically, if what? If the top of that fraction is 0. So let's take the top and set it equal to 0. And let me multiply this. That would be what? 2 here, v thevenin square r sub L times r sub L plus r thevenin to the 1st power. Move this one to that side. What do we have here? 2 times v thevenin squared r sub L plus r thevenin. Notice quickly some cancellation. What do you notice? Yeah, v thevenin cancels that v thevenin, and one of these, because there's 2 of them on this end and 1 on that, 2 here and 1 there. This cancels one of these. There's 2 of them there. So that's going to leave me with what? RL plus R thevenin equals what? 2 times R sub L. Bring the R sub L there. What do we have? RL equals R thevenin. For maximum power transfer, you want to make sure R sub L equals R thevenin. So if you want your power to be the most at the load, make sure R sub L equals R thevenin. See, calculus comes in handy here. Now let's look at it. Well, let's go back to this. We said the power is going to be that, right? So now let's let R sub L equals R thevenin and see what will happen to the math. How much power is going to be sent to the load? So what is that power? Let's calculate, go back and recalculate the power. So the power to the load, once you let R sub L equals R thevenin, is going to be, according to this equation, V thevenin over R Thevenin plus, in place of R sub L, we're going to write what? R Thevenin, right? Because we said for maximum power transfer, you want R sub L to equal R Thevenin. That's two of them. That would be V Thevenin over, that's squared here, R Thevenin, there's two of them. When you square it, 4 R Thevenin squared times R Thevenin, and one of these R Thevenin will cancel. This will cancel one of the bottom ones. So that will leave me with what? The maximum power transfer is going to be V Thevenin squared divided by 4 times R Thevenin. That's how much power is going to be delivered to that load.
Should we just remember that?
You should remember, for maximum power transfer, R Thevenin equals R load. That's the key. The rest you can derive, you know. You'll use that a lot, so you'll know it actually. You won't have a choice with memorizing it because we use it all the time. But if you remember that one, then you can derive the rest of it. It's not that, you know, so oh, these guys are equal, that's 2R Thevenin, you can find the current. Now let's take an example. I started that ugly problem early, throwing all the stuff there, and I don't want to give you numbers to it. So let me put in some numbers here now. There we go. That problem we did last time. You know what? I don't like those numbers. Too much writing. Let me go on the back here and see if I can find a nicer problem. Maybe more challenging. Okay. Here's the question. Determine. I want to go back to the book to try to find the ugliest problem I can find. Determine what value of resistance would absorb maximum power from the circuit and the next question, and what is the maximum power? And what is the maximum power? I'm making that up. The maximum power delivered to it. Delivered to it. And here's my circuit. Somebody already chopped it. We have a load there. We took it out. I can actually put that load back in. 0.9 amp. This is 100 ohm resistor here in parallel with it. We have a dependent current source of 0.1 Vx, and I'll give you Vx later. $50 ohm. $20 ohm. Voltage source 2Vx, same Vx. This is 10 ohm. So this is where my load resistor is going to go, right here. And this is Vx. So we're going to take this circuit right here, and Thevenize it. Now that means my Vx becomes the voltage across this one. This and this in parallel. So if that's Vx, this is really Vx right here too. They're in parallel. So I got to make sure I don't lose that one. I'm going to see if I can simplify some of this stuff. Go ahead.
I was just gonna say you can simplify the 150.
Exactly, I was going that direction. You know, instead of having 150, let's put them together. They're in parallel. 100 times 50 divided by the sum of them. And that's 33.3, 33 and 1/3. So it doesn't matter which one you draw first. You know what? Okay, that's all right. I drew that one first, I'm not sure why. 0.1 Vx. This will be what? 0.9 amp, no change to it. The two resistors here, when you combine them together, we say roughly 33 ohms, 33.3. 33 is good. I right thing that I changed my mind. 20. Two Vx. 10, and that's your Vx. Two equations by two unknowns, if you look at it. Does anyone know what the voltage right here is? We call it VA. Do we know what the voltage here is?
2Vx. No.
If this is your ground here, what is that voltage?
Vx.
Vx. Do we know what the voltage here is?
Negative Vx.
Yes. Negative Vx, because it says this end, it's 2 Vx lower than that one. So whatever this, subtract from it 2 Vx. That's a negative Vx. You can assign current any direction that you want. So you say, I'm going to assign current in these directions. KCL at this node. KCL right at this node. What is going to that node? Let's find the current going to it. I see the 0.1 Vx going to it. What else? 0.9 is going to it. Should equal the current leaving that node, which is what? This current, and that's VA minus nothing over the 33.3, or just 33 is good. And the other one leaving is that current, which is VA minus a negative Vx over what? 20. This is 33 and 1/3 here, right? That number, if you want to find LCD, if you want to be creative, That number is 33.3333, if you can see it right here, which is 100 over 3. So instead of having that written like this, you can write that 3 over 100. You agree with that? So it makes my LCD easier. Why? You multiply everything by 100. So if I multiply by 100, 10Vx plus 90 equals 3Va. This will be 5, right? Plus 5Va plus 5Vx. Move everything to one side. What are we going to have? 90 equals 90 equals what?
8VA.
8VA
5VX.
minus 5Vx. Okay. Now I need to find a relationship between VA and Vx. Can we find a relationship between them here? Between VA, that's the voltage right here, and this is Vx right there. Isn't this a super node right here? So if you define this current going to that node and this one leaving, if we do KVL at that super node, what is going to that node? VA minus a negative Vx divided by 20 equals the current coming down, which is what? Vx minus nothing over 10. Can I clean that one? Multiply by 20, VA plus Vx equals what? 2Vx. Oh, what do you know? What's VA equal to?
VA is equal to VX.
That's my first equation. This is my second one. So go back to this one. Replace VA with Vx. Ninety equals what? 3Vx.
30.
Vx equals 30. What's the big deal about Vx? Why do we need it? Because Vx is actually your V open circuit, right? When you cut that circuit right there, isn't that your V open circuit, the same as this one? So you have V Thevenin. So V Thevenin, now we need to find the Thevenin equivalent, is equal to the V open circuit, which happens to be Vx, which happens to be 30. So I need that value. I need to find the equivalent, Thevenin equivalent circuit, so I can tell you what R sub L should be and what the power should be. I need V Thevenin and I need R Thevenin. Now we need to find I short circuit. When you have independent, dependent sources, to find R Thevenin is V open circuit over I short circuit. So let's find I short circuit. Let me take my circuit so you get to see it here. We're going to put a wire here. And once you put a wire, what happens to that Vx?
It's gone.
0, right? Because there's a wire connecting that. So Vx is 0. What will happen to that current source? That's gone. Because 0.1 times 0 is 0. Current source to be 0, that means an open circuit. (100/3), that's what the 33.
Does that mean that 0.1 Vx is?
0, gone.
Does that voltage source become a short circuit?
That now, notice that's 2 times 0. That's a short circuit, yes. That's gone too. And what's going to happen to that resistor?
Gone.
When you put a wire here, that resistor is gone.
That's in parallel with
With 0, yep. And that's my I short circuit. That resistor is gone. Guess what? It's current division. That's it. You look at that circuit, it looks like this. If you clean it, now I'm looking for that current. I like that one. So what's I short circuit equal to? Current division, 0.9 amps, times, if I'm looking for this current, I have to use that resistor, 100/3, over the sum of them. The 20 is what, 60/3? And 100, that's 160/3. I mean, I'm doing some of the math in my head. 20 is equivalent to 60/3. And the 100/3, when you add them, that's 160/3.
5/8.
0.9 times 100 over 160. You said that's 5/8. So that's 9/10. If you like fractions, that's with a 0.9. This is 5/8. By 5, this is 1, that's a 2. So that's 9/16. If you have a calculator, go ahead and make life easy. Now, can I find what R Thevenin is for that circuit? So my R Thevenin is equal to V open circuit divided by I short circuit. We said our V open circuit, what was it? I forgot. 30? That's 30/1. Divided by I short circuit, which is what? 9/16. You do the math. 30/1 times 16/9. Again, if you have calculators, jump on them. 10, 3. That's 160 divided by 3, whatever that value is. I'm a big fan of the math, so I like the math when I have to do it this way. I'm sure most people hate that. So what does R sub L will have to be? For maximum power transfer, you want R sub L to equal what? R Thevenin, which is 160 divided by 3. Is that 53.3? I think it's 53.3, is it?
Yeah.
And what about the power? What's the power delivered to the load? What's the maximum power? We said it's V Thevenin squared divided by what? 4 times R Thevenin. I just derived that. My V Thevenin is 30 squared 4 times R Thevenin 160 over 3. It's 900 over, that's 640, I think. 16 times 4, is that 640? Yep. Do the math. 900 over 1 times 3 over 640. Can simplify by 245 by 232, right? 3 times 45, 3 times 5, 15, 5 carry 1, 3 times 4 is 12, 13, 135 over 32, which is what? I'm not sure why I'm in the mood today of fractions. Maybe trying to get you all confused. So that's 4.218 watts. That's the maximum power delivered to that load, or absorbed by the load. So that's the thing to remember. For maximum power transfer, you want R Thevenin to equal R load, and the maximum power to the load will be V Thevenin squared divided by 4 times R Thevenin. And we have one more topic left in the chapter. We will not be able to finish it since we only got 7-8 minutes left in the time here. And that topic, delta and y conversion. So I'll stop the video here. I'll assign some homework.